Good morning, children. Good morning. Hope all are there on the line. More than 20, I think. Now the time is 10:30. I think we'll begin the class. Isn't it? Can I get a wish from anyone? So let me know whether I am audible. Good morning. Good morning, children. Okay. Okay, good morning. Good morning. Okay. Okay, I just wanted to know whether I'm audible to all of you. That's all. Okay, children, I hope you remember what we have studied in the previous class. We were talking about metallurgy. And in the previous class yesterday, we have seen, as the class was yesterday, I think it may be fresh there in your mind. Because today, after that class, after our chemistry class, you might have attended only one class. That is today morning class. That means at 8:30, isn't it? No other classes. So I think whatever I've taught you may be there fresh in your mind. So what all points did we discuss yesterday? We were discussing on the different steps involved in the extraction of a metal from its ore. Isn't it? Various steps we have seen, and I hope you all remember it. Helena, can you please tell me? Can you please help me to recall the different steps involved? Okay, please tell.
First procedure is crushing and grinding.
Okay.
Then we have to check the concentration of the metal. Then
Not
roasting.
checking, that means we are trying to purify it. Okay.
Yes. Then roasting. Then
roasting
reduction.
and
Calcination.
along with roasting. Okay, roasting and calcination.
Yes.
Okay.
Then reduction. Reduction. Refining and final stage of purifying.
Okay. We have reduction and after that refining and you get the pure metal. Isn't it? So these are the different stages involved. Okay, good, Helena. Now, Mrinalini, can you please tell me what are the different methods to concentrate an ore? Mrinalini, different methods to concentrate an ore? I hope Mrinalini is there on the line. Okay.
Once more.
What are the different methods to concentrate an ore? We have studied
hydraulic washing.
Yes. Hydraulic washing.
Magnetic separation.
Magnetic separation.
Froth flotation.
Froth flotation.
And leaching.
And one more. Leaching. Okay, leaching, or it is otherwise called chemical method. Isn't it? Leaching or chemical method. These are the 4 different methods that we have learned to concentrate a given ore. Okay. Now, a froth flotation method. Froth flotation method is normally applied on which kind of ore? Glycine. Yesterday, I think, did I ask questions to Glycine yesterday? I think I didn't get him on the line. Did I? I don't remember. Glycine, are you there?
Yes, miss.
Okay, Marine Joy. Okay. Okay, Glycine, please tell me then.
This question.
See, what did I ask you? What did I ask you? See, which type of ore is normally concentrated using froth flotation method? Froth flotation method is used to concentrate which type of ore?
Sulfide ores.
Yes, sulfide ores. Sulfide ores. Okay. See, normally zinc sulfide, lead sulfide, all these are concentrated using froth flotation method. Okay. So I hope you all have gone through what was taught in the previous class. And let me tell you one more thing, children. From this section, section B, just go through the stages involved in the extraction of a metal from its ore. Okay, we have learned different stages as the first question was that. So just be familiar with all these steps and also please do understand what are the different methods of concentration. Okay, and among them, froth flotation method, please do understand that it is a method that is used for concentrating sulfide ores. Understand the difference between roasting and calcination. Now, regarding reduction of metal oxides to metals, I just have explained the reduction procedure based on the metal activity series. You may find many other points given here and there. Whatever I haven't explained in the class need not be, you need not give more importance to all those points which I did not explain, because you may find certain points like in page number 128, you may find certain examples like cinnabar, mercuric sulfide. It's heated with oxygen. It is roasted. And again, by the bottom of that page, you can see a note given. Okay, so all those points you need not give too much importance. And also refining of metal. Do understand what do you understand by the term refining of a metal, and what are the different methods to refine. We have studied distillation, liquefaction, and electrolytic refining or electro-refining. So please do learn all these terms. Okay, details of, whatever I haven't explained is not necessary. And again, I think concentration methods, principles are just mentioned, isn't it? Detailed explanation, procedure of how these concentration methods are conducted. How is it done? All such explanations are not required. Okay, just learn the principle, the method, name of the method, and the principle involved in it. Okay, so whatever is not explained in the class need not give importance to. Now, today we are moving on to the next section, which is the most important topic of this chapter. The most important topic of this chapter, and actually this chapter metallurgy is meant for learning this extraction of aluminum. Earlier, my dear children, once when this chapter was taught, actually this chapter consisted of many extraction procedures of extraction of aluminum, extraction of zinc, extraction of iron, all were incorporated in this chapter. But for you people, not only for you people, a few years before, all these topics were just exempted, and only extraction of aluminum is to be learned. So you people are all lucky to learn such a small or confined topic. Okay, so you need to concentrate only on the extraction of aluminum, and it is sure that you will be getting questions on it. No doubt, because it's such an important chapter with high weightage of marks. So now we shall move on to extraction of aluminum. So this also we'll just listen like a story and then try to recollect. It's very simple, easy to understand. Okay, so now we shall see what all details do you know about aluminum. Aluminum as a metal with atomic number 13. It's a metal with atomic number 13, and its mass number is 27. Isn't it? And what about electronic configuration? We know that it is 283. And what about its valency? It loses out its free electrons from the outermost shell during a chemical reaction, and its valency is +3. Okay, so these are the main points that we know about aluminum. And again, something more about aluminum regarding the position of aluminum in the periodic table. It belongs to the third group and the third period. Easy to understand, easy to remember. Third period, third group. Okay, now that is about the position of aluminum in the periodic table. And again, aluminum is said to be the most abundant metal on the Earth's crust. Okay, the most abundant metal on the Earth's crust is aluminum. And again, we know that aluminum has a great affinity towards oxygen. And because of this particular property of aluminum, it won't be seen in its free state. Aluminum will always be seen only in its combined form, almost in the form of its oxide, mainly in the form of its oxide, because it has a great affinity towards oxygen. Okay. Now again, it was discovered by the scientist Oersted. Okay. It was discovered by the scientist Oersted. So these are the main details. Oersted. Okay. So these are the main points that we have to know about aluminum, discovered by the scientist Oersted. And again, most abundant element, not seen in the free state, always seen in the form of its oxide, because of its great affinity towards oxygen. Okay, now we shall move on to the extraction of aluminum. See children, already we have said that aluminum has a great affinity towards oxygen, and because of this reason, aluminum will be seen, most of the ores of aluminum are found in the form of its oxide, but we do have one ore of aluminum which is not an oxide ore. And what is the name of that ore? It's cryolite. I hope you remember. Cryolite is sodium aluminum fluoride Na3Al F6. Okay, and we do have bauxite, it's a hydrated ore of aluminium. And again, we have corundum, it is anhydrous aluminium oxide. These are the three main ores of aluminium. Out of all these three ores, we have to choose the first one, that is bauxite. Bauxite, not cryolite. I said cryolite as the first one, but bauxite is the most common or the main ore of aluminium. Okay, so what is the formula for bauxite? Al2O3, Al2O3, 2H2O. The dihydrated oxide ore of aluminium. Okay, so this is the ore that is given to us. With this, we have to extract aluminium. Okay, now, normally once when bauxite is given to you as a ore, it will contain around 60% of the ore bauxite. 60% of the ore will be there once when it is obtained from the earth's crust. 60% of bauxite will be there in the given ore. The rest being sand, titanium oxide, ferric oxide are the other impurities that may be associated with the main ore. Okay, ferric oxide, titanium oxide, and sand. So all these are to be removed. All these are some kind of earthly impurities. You have to remove all these. So what can we do in order to concentrate this ore? Because we know we have to concentrate the given ore. Before that, we have to crush and grind it, isn't it? So what are we going to do? We have the ore, bauxite ore with us. It's completely filled up with a lot of impurities. Mainly 60% of the ore will be there once when we take it from the earth's crust. The rest, 40% will be of sand, ferric oxide, and titanium oxide. Now, what is the first step? We know it's crushing and grinding, or otherwise it's called pulverization. So we'll crush and grind the ore well. Okay, now it is in a powdery form. Now simply you're going to heat the ore. Just heat the ore. You have crushed and grinded it well. Now just simply heat up the ore. Why do you do this particular step? I mean, why are you heating the ore? Just to remove the volatile impurities. If certain kind of volatile impurities, like maybe moisture even, it just gets removed once if you're heating the ore before concentration. Have you followed? Now, what is the next step? After heating, now you have to concentrate it. We have learned 4 different concentration methods. Out of these 4 concentration methods, we are going to choose the last one, that is leaching or chemical method to concentrate the ore of aluminium. Okay, leaching is commonly used. You know what is leaching, isn't it? So, leaching is a method that we are going to apply here. So first of all, the crushed powdered ore is heated. Almost all the volatile impurities might have got removed. Now we are going to concentrate it. This method of concentrating the ore or concentrating bauxite ore or the ore of aluminium is called Bayer's process. What do you call it, children? You call it as Bayer's process. It is actually the purification process, purification of bauxite. Purification of bauxite is the first step. Purification of bauxite, or otherwise you can call it as conversion of bauxite into alumina. Conversion of bauxite into alumina. That's what actually happens here. Okay, purification of bauxite, or otherwise it's called conversion of bauxite into alumina. Okay, bauxite into alumina, and is given a common name, and that is Bayer's process. It's called Bayer's process. So you have to be familiar with all these terms. Purification of bauxite is the concentration of the ore that we do here. It's otherwise termed as conversion of bauxite into alumina, and the term that we assign for this conversion is Bayer's process. Now let us see how to work out or how to convert bauxite into alumina. So already we have crushed powdered ore. We have heated it to remove the volatile impurities. Now I told you that the chemical method that we are going to apply. So you are going to make this crushed powdered ore to dissolve in a particular solvent. That's what we call as leaching, isn't it? which is the solvent that we use here? Here we are going to use sodium hydroxide solution. We followed. Sodium hydroxide solution, we are trying to make this bauxite ore dissolve in sodium hydroxide solution, and it is heated under pressure to a temperature of around 140 to 150 degrees Celsius for about 2 to 8 hours. What all points did I tell you? It's very, very important. Okay, so what all things did we do, children? The crushed powdered ore, after heating, is now made to dissolve in a solvent, and that is sodium hydroxide solution. And once when we dissolve it in sodium hydroxide solution, what will we do? We'll just heat it. After making it dissolve in sodium hydroxide solution, we are heating that mixture under pressure to a temperature of 140 to 150 degrees Celsius for a time period of 2 to 8 hours. Okay, so this is what we call as leaching, making the ore dissolve in a particular solvent. And here the solvent that we have used is sodium hydroxide solution, which is a base. Okay, now we know that aluminium oxide, aluminium is an amphoteric metal. Aluminium oxide is amphoteric in nature. It's because of this particular property of aluminium, that is, as it is amphoteric in nature, aluminium oxide will be able to dissolve in sodium hydroxide. We have already learned amphoteric oxide or amphoteric metal is able to react with or is able to dissolve in bases, isn't it? Strong bases. So that is why we have chosen sodium hydroxide here. Now, so because these type of questions are seen asked nowadays. Okay, what is the reason? Why did we choose sodium hydroxide? Why can't we choose any other bases as a solvent to dissolve alumina? It's because of the amphoteric nature of aluminium. We followed. Aluminium oxide is amphoteric in nature. Now we make it dissolve. Now after 2 to 8 hours, what may be the reaction that might have taken place there? See, aluminium oxide, bauxite, with 2 molecules of water crystallization, is treated with sodium hydroxide solution. A temperature of 140 to 150 degrees Celsius is maintained. Time period of 2 to 8 hours is what we let this mixture heat up. Now, what are the products that you get? You get sodium meta-aluminate along with water. Sodium meta-aluminate. We have already learned this, isn't it? Sodium aluminium oxide is able to dissolve in sodium hydroxide. You get sodium meta-aluminate along with water. Follow. Now, one more point. See, bauxite is the ore. So we have learned that in leaching or in chemical method, the ore dissolves in the solvent, but the impurities will not, isn't it? So we do have some earthly impurities. Along with that, we do have some ferric oxide, titanium oxide, etc. as impurities. And those impurities will not get dissolved in sodium hydroxide. Have you followed? Only the ore gets dissolved in sodium hydroxide, and thereby what happens? The impurities will be settled down, and you can call it as red mud. We have learned about anode mud. Do you remember that, children? While we refine copper, while we try to refine copper from an impure bar, we have seen that impure metals will be, or impurities will be getting settled down under the anode, under the impure bar of copper, which is placed as the anode, and we named it as anode mud. Don't just mix up anode mud with red mud. Red mud is entirely different. Red mud is the impurities which are undissolved. Once when bauxite is made to dissolve in sodium hydroxide solution. Have you followed? So red mud, why do we call it as red mud? Ferric oxide, titanium oxide all give reddish color, or all these are red in color. So because of this, the coloration of the impurities that are settled down will be red in color. So that is why you call it as red mud. Okay, so now what can you do? Now you have dissolved sodium meta-aluminate with you. What is the next step? You can just filter it off. That's what we have studied, isn't it? We can just filter it off. All the impurities will be obtained as residue. You can just throw it off. Have you followed? Now the filtrate consists of sodium meta-aluminate. The filtrate consists of sodium meta-aluminate. Now the next step is we are going to dilute this sodium meta-aluminate by adding water and will bring down the temperature to around 50 degrees Celsius. Okay, the next step is we are trying to bring down the temperature to 50 degrees Celsius. Sodium meta-aluminate is hydrolyzed, or we can say that it is made diluted with water. Temperature is 50 degrees Celsius. All these conditions are very important. Sodium meta-aluminate is hydrolyzed, or otherwise you can say that it is diluted with water. And once when it is diluted with water, what all products do you get? You get mainly two products: a hydroxide of sodium as well as a hydroxide of aluminium. Okay, you have two metals in this compound. You get aluminium hydroxide and sodium hydroxide. Two products are obtained here. What about aluminium hydroxide? It will be obtained as a precipitate. Okay, so we have studied in the leaching method or in the chemical method, we have studied that once when we make the ore dissolve in the solvent, the filtrate will be consisting of the dissolved ore. Now the ore can be recovered by adding any other chemical reagents or any other substances to the filtrate so that the ore will be getting precipitated out. Here we are adding water. Simply water is added to the filtrate and the temperature is brought down to 50 degrees Celsius. Your aluminium hydroxide will be seen as a precipitate. It just settles down. Followed, aluminium hydroxide is obtained as a precipitate while sodium hydroxide will be in the solution form. Many other impurities will be getting dissolved in sodium hydroxide. Okay, so what can you do? You have the precipitate of aluminium hydroxide with you now. It can be again filtered. The filtrate will consist of sodium hydroxide solution with some dissolved impurities which can be reused for the extraction of aluminium. Have we followed? The sodium hydroxide will be the filtrate that can be reused for further reaction, for further extraction processes. Now, what about aluminium hydroxide? Aluminium hydroxide is obtained as a residue because it was a precipitate. And this residue is what we are in need of. Aluminium hydroxide that we get as a residue is washed well. It's dried. Then it is ignited. Ignited means it's heated to a temperature of about 1000 degrees Celsius. To a temperature of about 1000 degrees Celsius. So you're going to heat up. You are going to heat aluminium hydroxide, which you get as the precipitate. Aluminium hydroxide is obtained as a precipitate, is ignited to a temperature of about 1000 degrees Celsius. What happens? It gives you alumina, Al2O3 plus water. Okay, so this is what you call as alumina. Have you understood? So alumina is now ready with us. This is what we were trying to do, purification of bauxite. This is what we were trying to do. That means we have an oxide ore of aluminium. So water should be totally removed from that. So as a method to concentrate the ore, we chose which method? Leaching method. It's a conversion of bauxite into alumina, or otherwise called Bayer's process. What are the different steps involved in that? First of all, the ore that we have is crushed and grinded well. It's heated first. Slowly it is made to dissolve in a solvent, sodium hydroxide solution. Now this mixture is heated under pressure to a temperature of 140 to 150 degrees Celsius for a time period of around 2 to 8 hours. Okay. Now aluminium oxide, being amphoteric in nature, dissolves in sodium hydroxide, giving you a compound sodium meta-aluminate. Sodium meta-aluminate is further diluted. Okay, so sodium meta-aluminate is obtained by filtration, isn't it? Because we do have some undissolved impurities once when we make the ore dissolve in sodium hydroxide, so we do filter it. Now the filtrate is what we have as sodium meta-aluminate. So this sodium meta-aluminate is then diluted with water. Okay, temperature is brought down to 50 degrees Celsius, where you get a precipitate of aluminium hydroxide and sodium hydroxide. Sodium hydroxide will be left over there because we are filtering this mixture. Sodium hydroxide will be left over there as a filtrate, and that can be reused. While Aluminium hydroxide will be obtained as a residue. And this residue is washed well, dried, and then ignited to a temperature of about 1000 degrees Celsius, where you get aluminium oxide along with water, and this is what we were waiting for. So now bauxite is converted into alumina. I hope till here the things are clear to you. Okay, it's very important, Bayer's process. Now, once when we get alumina, which method of reduction can we do? Because we need to extract aluminium from aluminium oxide, isn't it? So what can we do? Once when we get a metallic oxide, almost everyone, we all have a tendency to make it react with any common reducing agents like carbon or carbon monoxide or hydrogen, so that the metal will be left behind and the reducing agent combines with oxygen, isn't it? So that is a normal method. But yesterday we have seen we select the reduction method according to the position of the metal in the metal activity series. The more reactive metals cannot be extracted by or cannot be reduced using common reducing agents. It cannot. Okay.
If aluminum hydroxide is heated in the presence of air, oxygen.
See, children, whenever any metallic hydroxide, we have already learned about whenever metallic hydroxides are heated, simply you have to heat it. Oxygen is not required there. Okay, because once when oxygen is added, what happens? There is no special product that is to be obtained. We are not going to get any change in the product. The only thing that we need is we just have to convert the hydroxide into its oxide. So whenever a metallic hydroxide is heated, okay, almost a stable metallic hydroxide is heated, what happens? It splits up into its oxide, leaving out water. So that oxygen is not required. Well, simple heating is enough so that the metallic hydroxide splits up. I hope it's clear because we have already learned a box. I don't remember in which chapter. Okay. Anyway, we have learned a box where we learn action of heat on nitrates, carbonates, I think in the chapter acids, bases and salts. Okay. Action of heat on various metallic oxides. Not oxides, hydroxides, nitrates, carbonates and all we have studied. So there, oxygen is not required for heating all these metallic compounds just because we are waiting for a decomposition reaction. When metal carbonate like calcium carbonate is heated, once when calcium carbonate is heated, it is undergoing a decomposition reaction, so you get calcium oxide and carbon dioxide. There, oxygen is not required. Followed. So this is also a decomposition reaction where aluminium hydroxide decomposes at a high temperature, giving you its oxide, leaving out water. I hope it's clear now. Is it not clear, children? That's why we are not using oxygen. Simple heating is enough. Oxygen, once when you add, the reaction will not be according to this because oxygen, once when you're adding, the only thing is an oxide, a higher oxide, all these will be formed. But we are waiting only for aluminium oxide, a simple oxide of aluminium, Al2O3. And it is a simple decomposition reaction. For decomposition reaction, we do not add oxygen. Okay, now here we have aluminium oxide. I told you, according to the metal activity series, the most reactive metals cannot be reduced by common reducing agents. So we go for electrolytic reduction. Aluminium is also a metal of that kind. Aluminium has a great affinity towards oxygen and it is highly stable, and simple heating of aluminium oxide will not leave out oxygen to leave behind the aluminium metal. And also, it cannot be reduced by using common reducing agents. Because of its strong affinity towards oxygen, common reducing agents cannot play any role. Okay, common reducing agents cannot play any role in removing aluminium from its oxide. So we have to go for electrolytic reduction of alumina in order to extract aluminium from its oxide. Okay, so again, scientists they decided, okay, aluminium oxide will be made to undergo electrolytic reduction. See, once when we have to make aluminum oxide undergo electrolytic reduction, what is the problem that may be faced by the scientists? They have to convert aluminum oxide into its molten form, isn't it? Because aluminum oxide is not going to dissolve in water, so it should be converted into its molten form. Once if it is converted into its molten form, it has to be heated, isn't it? Only then it gets converted into its molten form. So they tried converting, or they tried to melt aluminum oxide, okay, by heating it to a high temperature. And they found that aluminum oxide melts only at a very high temperature, that is around 2050 degrees Celsius. You have to heat it to a very high temperature. Aluminum oxide or alumina melts at such a high temperature, 2050 degrees Celsius. Okay, they were ready for that, but still there came another problem. At this temperature, aluminium started vaporizing. Aluminum oxide melts at a temperature of 2050 degrees Celsius, but at this particular temperature, aluminium from aluminum oxide, from molten aluminum oxide, started to vaporize, and it was seen to escape. And to collect the vapors of aluminium, which was evolved from molten aluminum oxide, was found to be a very tedious task. And it was at that time scientists decided, or they found it very difficult to extract aluminium, because the first thing is that high temperatures to be provided in order to make aluminum oxide convert into its molten form. But after all these efforts, once if they are trying to convert it into its molten form, at that temperature, aluminium is vaporizing out. If they were waiting for aluminium, but it vaporizes out very quickly at this temperature, and it's very difficult to collect these vapors of aluminium. They decided that it is going to be a rare metal, and it was very costly at that time. It was said to be very costly at that time because its extraction is very difficult. Okay, it was at that time another scientist, Hall, the scientist named Hall. Okay, Hall, he was actually a young boy who was working under his professor Herold, and he was trying various methods to extract aluminium from alumina. Okay, and it was after his long efforts, once he discovered, or once he was able to identify a particular thing, that is, he found that alumina, that is aluminum oxide, was found to melt, or it was found to melt once when it was mixed with another ore of aluminium, that is cryolite. Aluminium oxide, that is alumina, once when it was mixed with another ore of aluminium, that is cryolite. He found that this mixture of alumina and cryolite is getting converted into their molten form at a temperature of around 950 degrees Celsius. So from this, what did he understand? He decided to choose molten cryolite as a solvent for alumina. Did you understand, children? Molten cryolite was chosen as a solvent for alumina. So he just took some molten cryolite. Okay, around 60% of molten cryolite was taken. So that 20% of alumina, that is aluminum oxide, and around 20% of another compound, calcium fluoride, was also added. In the beginning, calcium fluoride was not added. Actually, in the beginning, once when he conducted the experiment, only these two components were there. That is molten cryolite, which acted as a solvent for alumina, and alumina. These two were mixed together, and he just started heating them up. And he found that this mixture is totally getting converted into their molten form at a temperature of around 950 degrees Celsius. And at this temperature, aluminium will not vaporize. He was so happy. He just went to his professor and said that, see, I have done such an experiment, and he just passed electric current through this particular mixture of alumina and molten cryolite. And he was so surprised to see silvery globules formed at the cathode once when he conducted the electrolysis of this particular mixture. He found silvery globules formed near to the cathode, which when tested was aluminium. Okay, so this was a great achievement, and as a result, soon after this, aluminium became a very cheap metal, and it was now it's of very common use even at home. We follow, children. So it is the great effort of Hall and Herold. Okay, Herold, that is his professor, also accompanied Hall for his achievement, and they worked together thereafter and tried the extraction of aluminium from alumina. Have you followed? So this was the attempt made by Hall and Herold in order to extract or in order to reduce aluminium oxide in order to produce aluminium. Have you followed, children? So now we are moving on to the electrolytic reduction of molten aluminum. Electrolytic reduction of molten aluminum. Okay, so now let us see what are the different requirements for the electrolytic reduction of molten alumina. As we all know, once when an electrolytic process is carried out, see, some of them are asking me whether the box is to be learnt or not. See, children, I told you section C. From section C, whatever I teach you, each and every sentence, whatever I've explained, are to be learned. Okay, and I told you this is one of the most important topics of this chapter. Okay, now what we were discussing, children, we started discussing on reduction of aluminium oxide. Now, what are the requirements? For electrolytic process to carry out, we need an electrolytic tank, isn't it? So, an iron tank, rectangular iron tank was taken as the electrolytic cell. And a rectangular iron tank was taken as the electrolytic cell. See, let me try to show you the diagram. I know that you already have it in your textbook, but still, let's have a look onto the diagram. Now, this is the diagram for the electrolytic reduction of fused alumina or molten alumina. So what all things do you find here, children? We have a rectangular iron tank. Rectangular iron tank is there. Now, this iron tank actually is provided with a sloping bottom. But in this diagram, it's not shown, but the diagram that you have in your textbook has a sloping bottom. Okay, why are we providing a sloping bottom? Because it's from the bottom part of this tank, molten aluminium will be taken out. Okay, you might have seen an outlet at the bottom part of the tank through which molten aluminium moves out. Okay, so the bottom part of this tank will be always placed as a sloping one. Now, here we have the electrolytic cell. Inside the rectangular iron tank, there is a lining. You can see a lining, and that is called gas carbon lining. Okay, it's called the gas carbon lining, and that acts as the cathode. Inside, you can see gas carbon lining, and that acts as the cathode. Have you followed, children? Now, it's written there as graphite cathode here. Actually, all these are forms of carbon. All these are forms of carbon. So just use the term that we have in the textbook itself. It's gas carbon lining that serves as the cathode. You can see inside the tank, there is a lining, black colored lining, where a negative sign is circled. Okay, so this is the gas carbon lining, which is serving the purpose of the cathode. Now, what is present in the electrolyte? In the electrolyte, we have three components mainly. The first one is cryolite, molten cryolite. Now, we have alumina. Okay, so cryolite will be acting as the solvent. So more amount of cryolite will be taken. 60% of cryolite will be taken. 20% of alumina and 20% of fluorspar. Fluorspar. It's not mentioned in the diagram. Fluorspar is calcium fluoride, CaF2. So these three components will be present in the electrolyte. Have we followed? Now the electrolyte is ready with us. Now on the top of this electrolyte, a bit of powdered coke will be sprinkled. Powdered coke will be sprinkled on top of the electrolyte. I'll tell you why are we doing all these. Now we have to maintain the molten form of these three components, or the molten form of this electrolyte, isn't it? So you have to heat it. Electrical heating is done so that the molten form of this electrolyte can be maintained at a temperature of around 950 degrees Celsius is what we provide. Okay, now what about the voltage? A low voltage of 5 to 6 volts will be made to pass through the electrolyte, and if the voltage goes high, there is a problem that there may be a decomposition carried out on one of the components or the major component, that is cryolite. Cryolite may be decomposed. So to avoid that, we are maintaining the temperature to 950 degrees Celsius. Not only that, the voltage is also made low. Now, let us have a look onto the anode. You can see thick bars of graphite anodes just placed into the, or just immersed in the electrolyte. Have you seen it? Graphite anodes are placed in the electrolyte. So this is all we have as the setup, electrolytic setup. Have you followed? So in the electrolytic reduction of molten alumina or fused alumina, we have a rectangular ion tank with a sloping bottom, okay? And inside the rectangular ion tank, you have gas carbon lining serving the purpose of the cathode. Now, graphite rods are placed in the electrolyte, which serves the purpose of the anode, and the electrolyte is a mixture of 20% alumina, 60% molten cryolite, and 20% fluorspar. Okay, now once an electric current is passed through this electrolyte, electrolytic reactions will be carried out. Okay, I'll show you all the electrolytic reactions. Now, after the process, see, once when the electrolytic reaction is carried out, molten aluminum will be getting settled or getting deposited towards the cathode, isn't it? So where do we have the cathode? As a gas carbon lining, we have cathode along the sides, or also along the bottom of this rectangular ion tank. You can see gas carbon lining serving the purpose of the cathode. So molten aluminum will be getting settled at the cathode. So slowly it reaches the bottom part and it moves out through the outlet. So this is what we normally do. Have you followed, children? Now, why are we sprinkling powdered coke on the surface? It's actually to prevent the loss of heat by radiation. Okay, because we have to maintain the molten form of this electrolyte. So in order to maintain that, we are trying to, or we just sprinkle powdered coke on the surface of the electrolyte. Okay, and what is the purpose of cryolite that we add? Cryolite is actually acting as a solvent. It's an excellent solvent in order to make alumina dissolve, or in order to bring down the fusion temperature of alumina from 2050 degrees Celsius to 950 degrees Celsius. Who helped? It's actually cryolite. Okay, so the role of cryolite is that it lowers the fusion temperature from 2050 degrees Celsius to 950 degrees Celsius, and it also enhances the conductivity of the electrolyte. It's very important. You should know what is the role played by the component cryolite. Okay, now what about fluorspar? Fluorspar and cryolite together, they are acting as a solvent for this electrolytic process. And not only that, we know pure alumina is almost a non-conductor of electricity. Pure alumina is a non-conductor of electricity. Have you followed? Because it cannot be converted into its molten form. Once if it is not converted, or once if it is not heated to a temperature of 2050 degrees Celsius. So it's not a good conductor of electricity. So because of that, in order to enhance the conductivity, what do we add? We add fluorspar and cryolite. Now, I also told you why are we adding powdered coke on the surface of the electrolyte. It is to prevent the heat loss by radiation. So I hope you have understood the role played by each and every component in this electrolytic reaction. Okay, so now we shall see how the reaction is. Now let us see the ionic equation. Ionic equation, because we have mainly three components: Na3Al(F6). Okay, we have Al2O3 and also CaF2. These are the three components in the electrolyte, isn't it? So how Na3Al(F6) undergoes ionization? We have Na3Na plus Al3 plus 6F minus. Don't make any mistakes while you write this. Okay. Now, aluminium oxide, 3Al, 2Al3 plus, because there are 2 atoms of aluminium. 2Al3 plus 3O2 minus. Isn't it? 3 oxygen atoms are there, so 3 oxide ions. Calcium fluoride, Ca2 plus 2F minus. Don't make mistakes while you write the ion. Okay. Now, these are the different ions present in the electrolyte. Now, what about the positive ions? We have mainly 3 different types of positive ions: Na plus, Al3 plus, and Ca2 plus. Among these 3 positively charged ions, which one will be getting the preference to get discharged at the cathode? The one which is lower by position in the electrochemical series, and that is aluminium, isn't it? So at the cathode, aluminium ions will be getting the preference to get discharged. Okay, we shall write the electrolytic reaction. Now, what about the negatively charged ions? Fluoride ions and oxide ions are there. Out of these 2, oxide ions will be getting the preference. Oxide ions will be getting the preference to get discharged at the anode. Have we followed? So electrolytic, ionic equation is this one, and from this we have chosen the ions which may get the preference to get discharged at cathode and anode. Now let us write the anode and cathode reactions. Okay, anode and cathode reaction. At the cathode, what is the reaction carried out? We know that it's aluminium ions approaching the cathode. Now at the cathode, which is the reaction carried out? Reduction. Reduction means gain of electrons. How many electrons? 3 electrons are to be gained. You get metallic aluminium. Okay. At the anode, what happens? It's oxide ions that reaches the anode. Okay. At the anode, it's oxidation carried out. Oxidation is loss of electrons. Loses out 2 electrons, giving you an atom of oxygen. An atom of oxygen has no independent existence. And not only that, we should never leave out the equation writing like this because it's a diatomic element. Not only that, we have already learned that during an electrolytic reaction, number of electrons lost should be equal to the number of electrons gained, isn't it? So we have to equalize the number of electrons on either side. So for that, here, 4 aluminium ions gains, 1 aluminium ion is gaining 3. So 4 aluminium ions are there. It gains 12 electrons, giving 4 atoms of aluminium. 4 atoms of aluminium. So you can equalize here with 12 electrons. We followed? Or you can start either from this side or this side, doesn't matter. So here also we have to make the number the same, the 12 electrons. If 12 electrons are involved, how many oxide ions? How many oxide ions? 6 oxide ions. Isn't it? 6 oxide ions. 1 oxide ion loses 2 electrons. So 6 oxide ions loses 12 electrons, giving you 6 atoms of oxygen, or 6 nascent oxygen atoms. 6 nascent oxygen atoms. 6 nascent oxygen atoms. Isn't it, children? So from the 6 nascent oxygen atoms, how many molecules of oxygen can be prepared, or how many molecules of oxygen will be formed? You can write it as 3 oxygen atoms and 3 oxygen atoms, giving you 3 molecules of oxygen. You get 3 molecules of oxygen. So these are the products that you get at the cathode and anode. So you have to equalize the number of electrons at both cathode and anode. So as a product at cathode, you get aluminium. As a product at anode, you get oxygen. See, children, at the anode, oxygen gas is evolved. Isn't it? We have seen that graphite rods are placed as the anode. Isn't it? So this oxygen atom goes and reacts with graphite anode. The reason is the temperature of 950 degrees Celsius is maintained there. So because of this high temperature, oxygen shows a tendency to react with graphite anode. First it forms carbon monoxide. Okay, and this carbon monoxide is further oxidized to give carbon dioxide. The reason is normally graphite is an inert electrode, but still here the reaction is carried out, or it's reacting with, or graphite anode is reacting with oxygen just because, what is the reason, children? Only because of one reason, the temperature is very high. Okay, and the components are placed in its molten form. Okay, now carbon dioxide will be formed at the anode, isn't it? Oxygen is actual product, but it reacts with anode and finally forms carbon dioxide. So this anode is to be replaced periodically because anode is actually reacting with oxygen, isn't it? So anode is to be replaced periodically. And I told you about sprinkling powdered coke on the surface of the electrolyte, isn't it? There are two reasons for doing that. One reason is to prevent or to avoid the heat loss by radiation. The second one is to prevent or to minimize the burning of anode. Here, as oxygen is continuously reacting with graphite anode, there is a chance for anode to get burnt. So in order to avoid that, powdered coke prevents this particular burning process. Followed. So these are the two reasons why we sprinkle powdered coke on the surface of the electrolyte. So I hope the exact extraction of aluminium process is clear to all of you. So we have studied, it's a very important point, children, it's very, very important. How many times I have to tell the importance? I don't know. So that's much important the topic is, so you have to give importance. Okay, so now we are just trying to recall what we have studied under this topic, extraction of aluminium. So we have seen that the first step is Bayer's process, or otherwise we can call it as conversion of bauxite into alumina. And in this process, what is happening? First, the crushed and powdered ore is first heated, made to dissolve in sodium hydroxide solution under pressure at a temperature of 140 to 150 degrees Celsius for 2 to 8 hours. Our ore dissolves, impurities will not. And the product that you get is sodium aluminate. Sodium aluminate is what you get as the product. Now, what else to be done? Impurities which will be left out as ferric oxide, sand, all these will be there. You call it as red mud that can be filtered off. Now, the filtrate is sodium meta-aluminate. The sodium meta-aluminate can be further diluted with water to a temperature of, bringing down the temperature to 50 degrees Celsius, where you get aluminium hydroxide and sodium hydroxide. Aluminium hydroxide is precipitated, so you have to filter it again. Now, this precipitate is washed, dried, and ignited to a temperature of 1000 degrees Celsius, where you get alumina. Alumina cannot be converted into its molten form under normal temperature. So, in order to bring down the fusion temperature of alumina, molten cryolite is added. Always use the term molten, very important. Molten cryolite is added. So, molten cryolite is acting as a solvent for alumina. Fluorspar is also added. Now, alumina, cryolite, and fluorspar act as the electrolyte in the electrolytic cell, which is an ion tank with a sloping bottom. Gas carbon lining serving the purpose of cathode, and graphite anodes are immersed in the electrolyte. Once when the electric current is passed through it, what happens? You can see at the bottom or near to the gas carbon lining, molten aluminum will be formed, which can be taken out through the bottom outlet. Okay, and at the anode, there is a chance for, oxygen is a gas evolved there. It reacts with graphite anode and forms carbon monoxide. Further oxidation of carbon monoxide makes it get converted into carbon dioxide. Because of this reason, it should be, anode should be periodically replaced. Okay, now in case as the reaction is carried out, as the reaction proceeds, the quantity of alumina in the electrolyte decreases. In that case, voltage, we are maintaining a low voltage, isn't it, of 5 to 6 volts. Once when the quantity of alumina in the electrolyte decreases, suddenly the voltage jumps to 40 or to 60 volts. So once if you are connecting the circuit to an electric bulb, when the quantity of alumina in the electrolyte decreases, a high voltage will be formed there. As a result, the bulb glows brightly. Once when the bulb glows brightly, it indicates or it just shows that the quantity of alumina in the electrolyte has been reduced. So you can add more and more quantity of alumina, or you can just try to maintain the amount of alumina in the electrolyte. Have you followed, children? So that is also an important point. You have to connect it to a bulb so that once when the quantity of alumina in the electrolyte lowers, immediately the bulb glows due to high voltage formed. Okay, once the bulb glows, you can add more and more quantity of alumina to the electrolyte and maintain the process. Okay, now I hope this point is very much clear to you. There are different points given separately, like roll of cryolite, roll of loose roll of powdered coke. All these are given in your textbook. You have to learn it thoroughly. Okay, after this, you can see refining of aluminium, which is not included in your syllabus. Okay, so what is this method called? Reduction of alumina, reduction of electrolytic reduction of molten alumina is named as Hall-Héroult process. What do you call it, children? It's called Hall-Héroult process. Hall-Héroult process. Very important. Hall-Héroult process. Okay, so Hall-Héroult process is the electrolytic reduction of molten alumina. And again, aluminium which is obtained after the electrolytic reduction of molten alumina may consist of further impurities and it can be refined, as we have done the refining process of copper. Okay, it can be refined, and it also has a different name which is not included in your syllabus, and we don't have to bother about it. Have you followed? So we have completed section C also, and you have understood the importance of the section. And from section D, we do have only 1 or 2 points to mention. Though it seems lengthy, there is nothing to be learned. What is an alloy? What is an alloy, children? You know it. An alloy is a homogeneous mixture of 2 or more metals combined. Isn't it? Or it may consist of 2 or more metals along with non-metals too in certain cases. So just learn the definition of an alloy, which is given in a box in your textbook. You already know what is the definition of an alloy. Don't miss out the term. It is a homogeneous mixture. Okay, now, and by the side, again, one more box, you may see what are fusible alloys. Fusible alloys. Fusible alloys are the ones with melting point ranging between 51 degrees Celsius to 260 degrees Celsius. They are called fusible alloys. Just be familiar with these terms, only the ones which I tell you. Okay, so alloys melting in the range of about 51 degrees Celsius to 260 degrees Celsius. These alloys are commonly called as fusible alloys. Alloys of tin, lead, bismuth, all these are considered as fusible alloys. Okay, now another term that I have to introduce, maybe you might have heard it, the term is amalgam. What's an amalgam? Amalgam. An alloy of any metal with mercury. An alloy of any metal with mercury. Maybe sodium forms an alloy with mercury. You call it as sodium amalgam. Gold with mercury, gold amalgam. Silver with mercury, silver amalgam. Okay, so whenever you hear the word amalgam, what should come to your mind? It's an alloy of a metal with mercury. The term is mercury. The most important should be given for mercury. An alloy of any metal with mercury is called an amalgam. And normally mercury does not form an alloy with iron. Iron is not going to make an alloy, or it is not going to form an alloy with mercury. So because of this reason, mercury is almost stored in iron bottles. So just note that point. There are 3 boxes in page number 133. Just learn all those 3 boxes. Okay, now after that, we don't have much things to learn. In page number 135, you can see a list of alloys given. You know what is the purpose of alloying? Isn't it, children? In order to increase the durability, to avoid wear and tear, and to make changes in the properties of a particular metal, we normally go for alloying. Isn't it? Gold is a very soft metal, and you cannot do anything with gold. if copper is not added to it. Once when copper is added, it makes an alloy of gold and copper. You can mold it into any shape, isn't it? So purpose of alloying is to just make the metal change its property and to make it useful for various purposes. Okay, so from this box, which you have in page number 135, please mark these alloys, only the ones which I ask you to learn, which I ask you to tick, are to be learned. The first one, duralumin, very important. The ones which I ask you to tick should be learned. Duralumin, please put a tick mark, duralumin. And learn only the composition and use of duralumin. It consists of aluminium, copper, magnesium and manganese. Aluminium, copper, magnesium and manganese. Learn it in the correct order. Learn it in the correct order because they may ask you sometimes to write the main components of this particular alloy, or otherwise they may ask you to write it in the order of their proportion. Sometimes they may ask you only the main component. Whatever the thing be, please try to learn it in the given order. Okay, because as you move down, their components proportions keep on decreasing. So you have to maintain this order. And the uses, the case of duralumin, it is used to make bodies of aircraft, buses and tube trains. It is used to make light tools and pressure cooker. That's all what you have to learn. And the next one, yes?
Do we want to learn the percentage?
Percentage you need not learn. Need not learn the number the number mentioned there. Learn it in the correct order. That's all. Numbers you need not. Okay. Now, stainless steel. An alloy made out of iron, chromium, nickel and carbon used for making utensils, cutlery, ornamental pieces and surgical instruments. Properties you can avoid. Next one is brass, consisting of copper and zinc. Copper and zinc, the main component. The question may be like that sometimes, okay? So always maintain the order. Copper and zinc, and just go through the uses. Decorative, hardware utensils, screws and handles, cartridge, containers, parts of watches and taps, musical instruments, electrical goods, marine, engine. Bronze, copper, tin and zinc. Used to make medals, statues, utensils, bearings and coins. And the last one, solder or fuse metal. Hope you are marking it. Solder or fuse metal, consisting of equal percentage of lead and tin, used for soldering purposes. And also to make fuse. Okay, soldering purposes, maybe you're familiar with. So these 5 alloys are the only ones that you have to learn. And that also composition, numbers you need not learn, but you have to learn it in the correct order. Good. And also learn the uses of these alloys. Okay, so with this, we have completed this chapter. So for the next class, I want you to find the answers of the exercise questions because we did not discuss that. Okay, also, please keep in your mind, tomorrow you have a test paper on the chapter electrolysis. Do prepare well for that. So thank you, children. That's all for today's class. Thank you so much.